that pictures presentation. By what name is it?
this one, ये वाला.
I just play it directly. नहीं अभी जब बोलूँगी तब कर देंगे.
एक मिनट, इसको ओपन कर दो. Moment we will see. Let him start.
A very good morning to all, and I once again welcome you to ION's Manipal 2019. With the hope that day one was wonderfully good, Manipal OSA student chapter is here to make day two even more happening. Did you all have fun during the activity hour yesterday? Can I have a louder one? Okay, so today is a special day as it is going to end with a blissful cultural night and a gala dinner. Also, the eminent speakers for today are Dr. Preetham Deb and Dr. Asima Pradhan for the scientific lectures. We welcome you, sir. We welcome you, ma'am. Also, we have a professional development talk by Dr. Dan Christensen during the second half. And we have oral presentations from the invited speakers. So before we start with the scientific talk, let us have a glance of the last 2 days through this small presentation.
Change it again. There's no sound.
Okay, so we have the pictures from day 0 and day 1, and you can have access to all of these pictures as they've been uploaded. You may scan the QR codes on your tags, and you will be directed to a drive from where you can take all these pictures. So I have some important announcements. I kindly request you all to pay attention. Today at 12:10 p.m., we have the official IONS Manipal group photograph. So I expect you all to gather at the venue. Also, the coupons for gala dinner will be available at the registration desk. You all have to go there and collect the coupons for the same. While you go for it, you have to register for the social day. Who's coming? For more information regarding the social day, you may go to the website, scanning this code, and you will get all the information about tomorrow. The poster presenters today are expected to put up their posters upstairs on the first floor, as the poster presentations will take place today evening. And so now we finally start with day one. We have a scientific talk by Dr. Preetham Dev, and I request Humera to take over the mic and introduce Dr. Preetham. Thank you.
Dr. Preetham Dev is a professor at the Department of Physics in Tezpur University. Dr. Dev has done his master's from Calcutta University and finished his PhD in 2003 from Jadavpur University, Kolkata. Dr. Dev has more than 70 papers in international journals, 5 patents, 2 software copyrights, and 2 books in his name. Some of his tremendous achievements include National Bioscience Award for Career Development, American Physical Society Professorship Award, Max Planck Fellowship, UGC Career Award, Young Scientist Award, and many more. Today, he will be sharing his knowledge on molecular imaging from molecular imaging from materials perspective. I would now like to invite Dr. Preetham Dev on the stage. Over to you, sir.
A very good morning to all of you. At the outset, it is a privilege for me to be here on the occasion of this Optical Society of America the conference, IONS 2019, and also in this Institute of Eminence, Manipal University. I would like to thank the organizer, Professor Satyamurthy, Professor Mahato, and Dr. Majumdar for giving me the opportunity to stand in front of you. As it has been already told, that today I'll be talking on the subject molecular imaging. As you all know, imaging techniques are gaining popularity because of its incredible visual representations. Biomedical imaging in particular is very important for these visual representations in the field of medical science. Scientists are trying hard and innovating constantly to have the advanced imaging techniques and state-of-the-art imaging capabilities in terms of developing imaging probes and the contrast agents. Coming down to molecular imaging, it's the imaging technique which involves the characterization, visualization, and the measurement of the biological processes at the cellular and the molecular levels. It provides very important insights in the human body, and also it gives important informations which other imaging techniques cannot provide. A molecular imaging technique basically depends on two aspects. One is the imaging device, and other one is the imaging contrast or the probe. When this imaging contrast and the probe is injected inside the body, they try to get accumulated around the organ or gets attached to the cells. The device will try to detect those imaging contrast or the probes, and then they try to get the distribution of these contrast probes for imaging particular organ or the cells of interest. Now, this pattern of distribution of the imaging probes will enable a deep insight into the cellular level informations for the physicians for the diagnosis purpose. Now, among many of these imaging techniques, as we all know, I need not have to explain, these are all in practice. Today, I am trying to focus my interest in magnetic resonance imaging and fluorescence imaging. You all know this optical imaging or fluorescence imaging, what I want to say, was recognized very recently, just a few years ago, for that Moener, Bettig, and Hell. They received the Nobel Prize for developing the super resolution fluorescence microscopy. This innovation actually enabled to bring this fluorescence microscopy or optical imaging to the nano dimension. If you see the other side of this imaging capability in terms of magnetic resonance imaging, it's a long history. Rabi, Bloch, Purcell, they developed the nuclear magnetic resonance. And then Paul Lauterbur, he developed the technique called magnetic resonance imaging in 1971. He was awarded the Nobel Prize for the development of the concept of gradient magnetic field for having the spatial resolution. Then, in the same year, Peter Mansfield was given the Nobel Prize for his theoretical formalism of this magnetic field gradients and fast imaging capabilities. So, I mean, these two fields are developing in their own way with better capability of the contrast, and the research is still active in this area. Here I try to see the sensitivity of the imaging along with their spatial resolution for different imaging capabilities. So, as I have already mentioned to you, I have the interest in today's talk on the magnetic resonance imaging and the fluorescence imaging, combining these two functionalities in a single entity. So if you see the sensitivity wise and the spatial resolution wise, these two imaging capabilities have their own merits and the demerits in different regions. And we are trying to combine them into single entity. Now, this will enable us to get the good contrast between the soft tissues of the body. It can be able to image brain, muscles, heart, and other organs of the human body. Of course, it is non-invasive and no use of ionizing radiation in this sector. Now, I will spend a few minutes on these two aspects of imaging, MR imaging and fluorescence imaging, before coming to the interesting results what we have obtained. I hope all of you have seen, because this is now very important imaging device in the medical sector, MRI. It consists of a big magnet with a bore where the patient will be placed in the gradient magnetic field, and depending on this gradient of the magnetic field, you will have contrast of different parts of the body. Now, there are two magnetic coils in this magnet, primary magnetic coils and the secondary magnetic coils. So primary magnetic coils will have the spin alignments, and the secondary magnetic coil will provide the gradient magnetic field for having the imaging capability. As I have already mentioned to you, this magnetic resonance imaging is based on the principle of nuclear magnetic resonance of the protons. Now, if you consider our body, it's full of water. Almost 70% of our body is full of water. And water molecule will have the magnetic spins, two magnetic spins. And when you apply the magnetic field, say B naught in the magnitude, then you will have the quantization of the spin states in a polarized way. Now, the number of spins accumulated in the lower energy states will be say ppm level more than the higher energy states. Now, what the imaging capability does is that, taking advantage of this difference in the population of the spins at the two energy states, or the energy level difference, we try to image that accumulated region of the organs in the human body, or the cells in the body. Now, the problem is that, as I told you, the difference in the population of the spins at these two energy states is very low. So what we have to do now to enhance the sensitivity, we're applying the RF pulse in the direction of X. So which will make the the rotation of the spins in the XY plane going away from the Z direction. Z direction, please remember, is the direction of the applied magnetic field. So it will be precessing around the Z direction. Now, you withdraw the RF pulse. That means you turned off it. So these electrons, they will try to come to its original direction, that is the applied magnetic field direction. Through this process, the relaxation occurs. And this relaxation path occurs in two different ways. One is called spin lattice relaxation, or in terminology, we call it T1 relaxation. The other one is called the spin-spin relaxation, that is T2 relaxation. So basically, T1 relaxation is the positive contrast, will give you the brighter contrast, and T2 relaxation is the negative contrast that gives you the darker contrast. And that's the way you play with the contrast by this application of the RF pulse and switching it off. Now, the thing is that the question might be coming, my dear students, you might be thinking at this juncture that we have the water inside our body throughout. Now, how do I differentiate the signals for different parts of the body? So for that reason, because all the water molecules and their associated spins will relax in the similar fashion. Now, how to differentiate the signals? So what we do, we have the gradient magnetic field applied in addition to this static magnetic field. So this gradient magnetic field will enable you to have the contrast in the image. So the picture what I showed you, the magnet with a bore, the huge magnet, it will have a primary coil and a secondary coil, and two coils will be responsible for these two different magnetic fields applied. And a particular region will be identified inside this coil where the magnetic flux will be maximum. So the portion of the body what we want to image in this particular field, the patient has to go through that region or to that region, and the image will be taken accordingly. So I have tried to show here that with the application of the gradient magnetic field, how you can have the variation in the contrast for imaging. Now, now when you relax the RF pulse, that means you withdraw the RF pulse, then you will have the emission of the radio waves. The emitted radio waves will have the Fourier transform, and then you get this kind of pictorial representation of the MRI image. Next thing is that, since I told you that the difference in the population level is in the ppm order, now it cannot resolute the complexity of the arrangement, spatial arrangement of the organs inside the human body. So this is a serious, shortcomings in the MR imaging at a point of time. Then what was suggested, that if you will inject a contrast probe or the contrast agent, which will get accumulated to your target specific organs, and then they will start interacting with the water photons. And because of this interaction, you will have different relaxivity because of the contrast agent and the water photons. So you will have a better resolution in the contrast by injecting these MRI contrast agents. So other aspect of how to achieve the better contrast agent through this, better contrast through this contrast agent is that when you apply these contrast agents, the T1 and the T2 relaxation times will get decreased. As a result, the T1, R1 and R2 relaxivities. Please remember, the R1 is the inverse of T1, R2 is the inverse of T2. So they will increase significantly. So your darker contrast or the brighter contrast will improve by injecting these contrast agents and interacting with the water photons inside your body. Some of the popular contrast agents in these aspects are gadolinium based, which are commercially available, iron oxide based, etc. Or some other paramagnetic metal ions, manganese based, something. So this is one of the commercially used contrast agent for the purpose, and these are the images using this contrast agent. As you can see, some of the areas are contrasted to have the better understanding of the sites. There are several contrast agents in the market available. I have tried to list them, but the thing is that if you look into the T1 and T2 relaxation, or in other words, the R1 and R2 relaxivities, the most important parameter for deciding which one is the most efficient contrast agent is the ratio of R2 and R1. And this ratio should be in the range between 3 to 10 to have the best contrast or the relaxivity. So this is one of the major challenge in front of this contrast agent developing community, to have the contrast in the range R2 by R1 ratio in the range of 3 to 10. The other one is, of course, the toxicity associated with the contrast agents when you are injecting them inside the body. So people are trying newer contrast agents, like we have also done this manganese-based contrast agents for its contrast efficiency. Now, if you see the history, the first contrast agent in the history developed was gadolinium-based complex, and the contrast, as I was telling you, when you put the contrast agent, it will interact with the water protons and will give the contrast after injecting inside the body. So you see, how these different parts of the brain can be resoluted in a very complex architecture. It can be resoluted by using the contrast agents. So the question can come that what kind of contrast agents are normally being used medical science. Paramagnetic metals, as I have told you, this actually gives the T1 shortening. So you will have the brighter positive contrast. And other side, you have the super paramagnetic nanoparticles of T2 shortening, which will give you the darker contrast. And if you see in the other side, the two imaging capabilities we are trying to integrate is the proton MRI and the fluorescence imaging. They are having their own advantages and disadvantages in terms of their resolution, the cost, the time for image acquisition, and many other parameters. So we thought of complementing these two imaging techniques in a single entity to have the broader range of the resolution, sensitivity, cost, and the image acquisition time. So this was the main motive for us. The question may be coming to your mind that how to measure the T1 and T2 relaxivity. So you please remember that with the RF pulse, we have the spin excited, and then we have withdrawn the RF pulse, and they are getting relaxed in different pathways. So when you have the 63% of M0, you will get the T1, and 37% of the applied magnetic field, you will have the T2 relaxation. That's the way the T1 and T2 is measured. And then you take the inverse of this T1 and T2, you'll get the relaxivities. The other imaging capability, what is in my consideration, is the fluorescence imaging. In contrast to the MR imaging, if you take the fluorescence imaging, it can image very specific features in a very small dimension in the body or in cellular level. Also, it can have the 3D features at the very small scale. So it's basically, you have the probes which will have the absorption, and then you will have the excitation and emission from those probes. And these emissions are helping you to resolute the informations there at deep inside. There are many fluorophores developed in last few decades. The most prominent among them is the candidate called quantum dots. I hope you know the features of the quantum dots. When you try to reduce the dimensions of the semiconductor particles from all the 3 dimensions, then it takes the geometrical shape of a dot, and because of this confinement, we call it as quantum dots, and it will have the tunability in the emissions. So basically, without changing the structure, compositions, and any other things of the material, when you vary the size, you have the modulations in the band gap, and that's why you have the emission tunability at different ranges. I have shown here with the example of CDSE quantum dot nanoparticles having the emissions at different wavelengths lambda. And then we have tried to see it in cellular level with different excitations, and different color emissions are coming out of it. What in our group, we are trying to do is to incorporate the nanotechnology in getting the high and higher efficiencies in this MRI and the fluorescence contrast probes. So briefly telling about the introduction of this technology, all of you know that if you look into the history of the technological developments, there is a beautiful correlations. And this revolutionary technologies come twice in a century, which completely changed the concept and the applications of the technologies. Recently, we are in the technology domain related to IT. Now we have entered into the technology domain called the nanotechnology. A long way to go. Introduction of the technologies scale, we are then widespread absorption, end of rapid growth phase. So what I want to say that a lot can be done using this technology. And very important thing is that in this technology, you are playing only with the parameter called the size. All other things remain unchanged. The most recent and the most important applications are being realized in the field of nanobiotechnology. For example, the imaging, diagnosis, therapeutics, drug delivery. These are the fields of recent interest for the community. So we are also trying to incorporate this materials and their technology in developing the imaging contrast and the probes. So, for example, I will pick up the example of MRI contrast. So, if you see the T2 contrast, then the relaxivity R2 is dependent on the magnetic moment of the particle. Now, when you are reducing the dimension from a bulk dimension to the nano, your magnetic moment and other magnetic properties are getting modified in a significant way. So, one can play just by varying the size of the nanoparticles to be developed for the contrast, having better and better relaxivities. Also, the surface spins accumulated play a major role in determining the magnetic moments. I'm not going into the details of that because that is a different subject for discussions. Now, what we are trying to do in integrating these two imaging capabilities is, several approaches we have taken. One of the approaches that we have taken the magnetic nanoparticle as the core and developing the fluorescent probe over the core, and then we are using it as the imaging agent for fluorescence and MRI. The other approach what we have taken is that playing with the surface engineering, we are taking the magnetic nanoparticles in a very confined form by using the capping agent, and then transforming the surface from hydrophobic to hydrophilic and conjugating two different entities into a single entity, the magnetic and the fluorescence. In the third approach, what we have done, we have taken the magnetic nanoparticles and the quantum dot particles inside a shell, and this shell will have the porous architectures. So the fluorescence and the magnetic imaging is integrated into the system, and these pores are actually acting as the path for the water accessibility, because the water has to go and come into contact with the magnetic nanoparticles for its relaxivity. So the porous architecture is very important, and we have, I will show you some of our glimpses of the results where we have developed the radial ports with ordered structures. So the first system what I am going to talk with you is called the magnetofluorescent hybrid of fluorescent dye and superparamagnetic iron oxide nanoparticles, having the ordered and radially distributed porous structure. So in very brief, the way we have developed the material, we have taken the oil water emulsion and then using the CTAB, and then we have evaporated the chloroform from the matrix. So this CTAB is creating the channels through the silica, and the radial ordered pores are getting developed in the structure. Then we have studied in detail the emission profile of this system, and as well as the MR imaging capacity of the system. The quantum yield of the system is not getting compromised even after getting conjugated inside the shell, and the relaxivity property is quite significant within the range R2 and R1 within the range of 3 to 10. So this can be a good candidate for the relaxivity. This is the complex, the structure fluorescence complex we have developed, and the size and shape of these shells are very uniform, having the radial pores distributed in ordered way. The other system what we have developed is a kind of platinum, cubic platinum and FEPT combined structure. So the idea behind it is that FEPT can be used for the MRI relaxivity of the system, and the platinum can be used for the ROS generation, reactive oxygen species generation, for cell death of the target specific sites. So it's a kind of iron platinum nanoparticle system to harness the multifunctionality in a single entity. Now, the thing is that, well, these are all structures related to the system. As you can see, the relaxivity profile showing its high relaxivity of the system, and this is applied in the mouse liver abdomen. So this contrast system, the multifunctional contrast system, is injected through the tail of the mouse in the vein, and then the accumulation is observed in the liver. And as you can see here, the clear contrast of the accumulated nanoparticles is being observed of that specific site. For understanding or for ensuring the the therapeutic part, what we have done, something very interesting, is that we added a non-fluorescent probe, DCPH, and then because of this ROS generation by H2A2 decomposition, actually we are trying to mimic the cell activities. So they will cause the cell death. So you can have the functionality of killing the cancerous cells in that procedure. And this was confirmed by this transformation of the non-fluorescent probe to a DCH fluorescent probe from this study. The relaxivity value is quite significant, as I mentioned to you, for this purpose. So it can be a good candidate for this multifunctional imaging probe. And another contrast probe of bimodal type, where we have developed this FEPT nanoparticles and CDS nanoparticles together in a system. Basically, what we have done, this FEPT nanoparticles are first developed within the TGA capping, and this has been used as the template to grow the cadmium cadmium layer. And then we have capped it with glutathione and given the appropriate reaction conditions. So the sulfur from this capping agent is getting attached to the cadmium and forming the CDS layer over the FEPT. Again, the fluorescence capability is not compromised, and the imaging capability is quite high. It's above 530. The commercially available contrast agents at the moment is giving the relaxivity near to 200, below 200, something like that. The quantability is also retained, and the lifetime has been measured, which is also not getting compromised after getting attached with the FEPT nanoparticles. In another system is called the multifunctional nanoplates of europium doped gadolinium oxide, having the strong red emissions and also a very high magnetic relaxivity, in addition to the drug releasing capability. So three functionalities we have tried to integrate into a single system. So this triangular shaped nanoplates of europium doped gadolinium oxide was capped with folic acid, and I will come to the functionalities in the next slide. Then the structures are very uniform in that aspect, as you can see from the microstructural characterizations. And they have a very high crystallinity, and europium content is something about 5.5 atomic percent. So that's why we named this europium doped gadolinium oxide. And then when we studied the relaxivity properties, though the T2 relaxation is low, but the R2 by R1 ratio is quite significant within the range of 3 to 10. So it can be a good candidate for relaxation MRI imaging. The emission capability is very strong, I have mentioned. The drug releasing, we have taken two drugs, hydrophobic drug donorubicin and the hydrophilic curcumin. And we have seen that with the variations of the pH, the drug releasing capability is varying. So it's a very efficient candidate for carrying the drugs and releasing to the target. So then we have also studied their efficacy in the cellular level, and this cellular level of these KB cells we have taken into considerations for the imaging with different excitations having different emissions of these systems. These are few of the systems we have developed in recent times, and quite a good number of publications came out of these studies. Almost 3 patents we could file of this MRI contrast, the dual mode contrast probes of MRI and fluorescence imaging. We have been working also on the future aspect in this biomedical imaging part. The future goal, of course, for the peoples to achieve is to integrate different imaging capabilities into the one or single entity. Like I have already discussed one example of theranostics, that means therapeutics and diagnostics incorporated in a single system. Different imaging capabilities, MRI and fluorescence in a single system. The different capabilities of MR imaging, T1 and T2 into a single system, and also drug carrying to the specific sites, releasing it there, having the fluorescence, and then the MR imaging. So all these functionalities combining into a single system is a kind of research goal for the scientific community to achieve. Some success in this direction have been achieved in our group also. Like one, I cannot disclose these results because we have just filed the patent before my coming here. The thing is that we are taking a genus system where the T1 and T2 is combined into a single system. So earlier, you can ask me the question, what is the advantage of having this, integrating the functionality into a single system? Actually, no single contrast probe can give you the desirable contrast resolution of your target specific sites. So people are trying to integrate different imaging capabilities and then inject inside the body. The other advantage of it will be, if you are injecting different contrast agents inside the body, it may be harmful for your body, but if you can integrate all the imaging capabilities into a single system and inject inside your body, you'll have the less toxicity issue in your body. So this is the main idea behind integrating the imaging capabilities. So in this aspect, the present technology is that people are developing T1 contrast agents or T2 contrast agents. What we are doing, we have developed a genus nano system, where genus means you have two different surfaces having two different functionalities, but it's a single system. So we have incorporated the T1 functionality in one side and T2 functionality in the other side. And then we have seen its imaging capability in terms of relaxivity and the contrast, and we have got excellent result in these aspects. So these are some of the future directions of the multimodal imaging and multimodal diagnostics and therapeutics in the field of biomedical imaging and diagnosis. So I have come to the end of my talk. I would like to acknowledge the students who have worked with me in these areas, and also my collaborators at different institutes who have actively participated in the research in all these directions. I would like to acknowledge the funding agencies who have been supporting me in these ambitious projects to me, DST, DBT, DAE, UGC in this aspect. UGC, of course, not in terms of the project, is giving me personal support for having the career award to pursue the research in this direction. Recently, I've got the same career award from DBT to pursue the research in this direction. We have also got the funding support from the external funding agencies like American Physical Society, DFG, Max Planck Society, and Newton Fund to support some of our activities. UGC DAE has supported for understanding the structural behavior of this complex structure, what I have described to you. And IUSSTF is also giving fund to us in terms of projects and collaborative center developed in my university. Thank you very much for your kind attention.
The session is now open to questions. Any questions from the audience?
Thank you very much for your talk. So what are the pharmacokinetic profiles of some of these nanoparticles? Where do they go? What's the uptake? What's the clearance? What's the biological biodistribution?
Yeah, these are very relevant questions. I mean, their uptake and the clearance. Though I was trying to concentrate on the uptake part and their accumulation at specific sites, because I modified the surface. That part I have not discussed here. Modified the surface with target specific proteins and antigens so that they will get accumulated at the specific sites. But the clearance part, I must tell that I have not studied that part. But since recent times I am in dialogue to transfer these patented technologies to the industry. So they have agreed to take up all these issues and study in details. So at this moment, of course, this release part we have not studied. Probably in future we'll have the detailed results. Yeah, please.
So, yeah, sorry.
So actually there is a relation between delta X and delta P in the quantum nature. So what do you expect from that? If you are squeezing that state space to certain limit, what do you expect in the momentum state?
Consider that. No, see, the thing is that, as I have already told you, that the semiconducting materials in a confined state, they will have the tunability on the band gap, and hence you will have the tunability on the emission profile. So when you have this confinement at a very small dimensions, your emissivity will increase in a significant amount. So when you are using it, as I have shown you some of the examples, if you see the quantum yield and the application in the cellular levels, there is certain amount of difference, and it is obvious because of the quenching. So if you start from a very high quantum yield fluorophores, then even after application in the cellular level and the quenching, you will have the sufficient amount of emission from the system so that you can have the visualization of the complexities.
I had a question.
Yeah, sure.
you said that you worked on cell mimicking systems, or you
Yes.
worked with cells.
No, 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 no. It's a cell mimicking means H2O2. It's getting decomposed and forming the reactive oxygen species.
Okay, so
And
so
yeah,
you have seen how it works with cells, or
yes, yes, yes,
okay. And
yes.
what about tissue? I mean, when it comes to
No, we have
actually,
not studied.
you have not studied.
I have not
So,
studied. I have studied only in the cellular
okay,
levels.
so when it finally comes to, you would actually let it go through the bloodstream, or and then see the
No, no, no,
accumulation, or
no.
how
What
would
I have done, I have taken the cells in the petri dish.
right? You would have done that,
Yeah, yeah.
but the eventually what is?
Yes, that's precisely the same answer I will give.
Okay, you're
That
saying
I'm transferring this technology to the industry.
so they
So
will-
we are in agreement. So they will take up these things.
Right.
And
Okay. Thanks.
Thank you, sir, for such an informative talk.
thank you very much.
I would now like to call upon stage Dr. Fujin Kao, Professor, Institute of Biophotonics, National Yangming University, Taipei, Taiwan, to present a memento as a token of gratitude on our behalf to Dr. Dev. Thank you, sir. We now have an oral presentation by B.S. Bhargav Ram from IIT Delhi. He'll be giving a presentation on spin orbit beams, the role of spatial and polarization modes of light. I kindly request you to be on stage.
Am I audible? Sorry for the inconvenience. So today I'm presenting that my PhD talk. It is on spin-orbit beams and the spatial and polarization modes of light. So usually these spatial modes are of optical vortices we are using, and the polarization is, as you know, it is the one of the degree of freedom of light that you can manipulate with using with wave plates and all. So this is my outline. So I'll be talking about what are the degrees of freedom of light, which can be used to manipulate the light field at any particular z plane. And these are the spatial modes which are actually having an orbital angular momentum of light, which is associated with optical vortices. And as you know, these polarization modes usually this is called linear polarization states and circular polarization states, where the circular polarization can carry spin angular momentum of light. This can be used as a carrier information in communication. So we are actually combining these orbital angular momentum of light and the spin angular momentum of light to get a spin orbit beams, which is a non-separable state. Means the spin of the light beam and the polarization mode, that the orbital angular momentum of the light beam cannot be separated. So that leads to some singularities called polarization singularities. So we are studying the diffraction properties of those spin orbit beams, and we saw some degeneracy in the intensity patterns. So we found some applications in using those degeneracy, and we use those spin orbit beams in optical image processing, mainly in edge detection. So in optics, wherever you go, you find this. This is the expression which is you usually express your electric field with this expression. But when you are going to see in clearly, this part will take care of the polarization, and this part is the amplitude, which is a spatial dependent, and this is the phase, which is also a spatial dependent. So these are the three degrees of freedom that can be independently manipulated to electric any electric field at any z plane. This is another equation you always encounter. This is the paraxial Helmholtz equation, on which if you are substituting this equation on this, you will end up with the, if you are using Cartesian coordinate system, you will end up with the HG modes, and if you are using cylindrical coordinate systems, you will end up with the LG modes. So we are talking about this particular phase constant, e to the power exponential of e to the power of IL phi. This is what makes the LG modes are very prominent contents in the optical communication and material processing and whatnot. So these are the HG modes, and these are the LG modes. And if you look at into this particular portion, the phase of the these beams is actually varying from 0 to pi. There is only two quantization into 0 or pi. But if you are looking into the LG modes, you can see a continuous variation from 0 to 2 pi, which makes these modes are very prominent. So what that phase actually? This phase can be realized using a spiral phase plate, which is a physical element having a the thickness of the material can be varied in azimuthal fashion like this. And if you imparting a plane wave onto this, you will end up with a phase variation like this, 0 to 2 pi. Or if you are counter rotating the spiral phase plate and eliminating the plane wave, you will end up with a negative phase. Likewise, if you have a two steps like that, one is going in the spiral way and the of the way, and it is taking another spiral way, you will end up with a phase variation of 0 to 2 pi, 0 to 2 pi. This is called a M is equals to 2 charge vortex. So the wavefronts are the helical wavefronts which are going in this way, in this fashion, like a screw. So the wavefronts will be a continuously, if once it is started till the infinity, it is continuous manner, it will propagate. And these having some these phase gradients can be taken with the integer called m. If you are having from 0 to 2 pi, then this will end up with a 1. And if you are having a 0 to 2 pi twice, this m is equals to charge 2. You can call it as a charge 2 vertex. So what are the applications of this? So this is having a orbital angular momentum imparted onto the any particle if you are illuminating with these kind of beams, and this can be used in interferometry, optical image processing, and also in communication, multiplexing and demultiplexing. Especially I gave an example here. usually a concave surface and a convex surface both will show the degeneracy in the intensity interference pattern here. So the concave and convex both will show, but when you are using this kind of beams as the reference beam, then you will end up with a spiraling in or spiraling out kind of interferograms, which actually removes the degeneracy in the interference. So the same can be applicable here also. This is an interferogram of a biological cell taken with a plane wave reference. You will see, you cannot see that whether it is a peak or valley. But if you are using this kind of beams, you can see that a peak and valleys can be easily discriminated. So now the other concept of light is accept of the light is polarization. So this part, so this can be represented as expolarization in the linearly polarization modes and bipolarization. But if you are combining these two with a little bit of mathematics, you will end up with a ellipse equation, which is in the form like this. So depending upon the delta, which is the phase difference between Ex and Ey, this will end up with a elliptically polarized light. Usually general polarization is an elliptical polarization, but that elliptical polarization can be degenerated into two ways. One is circular, one is linear. If this is the major and minor axis both are equal, then you will end up with circular polarization. But if you are this ellipticity, if it is squeezed like this, then you will end up with a linear polarization. So we will use this concept in when I come to the polarization singularities. But as of now, that information is sufficient. So as I told, this delta actually makes whether it is linear or circular polarization. And I told that this circular polarization imparts a spin angular momentum onto the particle, which it transfers to the particle. Spin that plus or minus h cross per photon. So this also can be used in interferometry, material processing, and all, and quantum information also like qubits. So how to represent these polarization states. So this is the Poincare sphere on which you can actually calculate. These are the S1, S0, S1. These parameters are actually physically accessible parameters, which are actually intensities. And you can represent, if you take the S1, S2, S3 as the coordinates of the system, and you can represent any polarization on top of the on the surface of this sphere, like this. Here the circular polarization, left circular here, and right circular will be here, or like this. So horizontal and vertical can be represented on either side of the sphere, like that. So till now we are talking about only this Ex and Ey, both are all actually a plane waves. But if you somehow create a spatially variable phase onto this Ex and Ey components, then you will end up with having a spatially inhomogeneous polarization distribution. How we can do that? So let us say a right circularly polarized wave with a vertex of charge, let us say for example, and a left circularly polarized beam with a vertex of charge -2. When they are both are combined, then you will end up with a kind of polarization distribution which is spatially varying. Like radially polarization, it is all outward, and this is azimuthally polarized. How we can create in reality? So you use a plane beam, import into the incident on the PBS, and one beam will comes here with the same polarization. The other beam will go and comes with the orthogonal polarization. These two are combined here with a quarter wave plate, which makes this left circular and right circular polarization. But see here, we are using a SPP, which is a spiral phase plate. I told that, which is having a helical nature. One beam is going from this way, will take the e to power of im pi value. This beam is going in this way, it is the e to the power of minus im pi value. Then both are combined here, you can create a spatially varying polarization distribution. So what is the advantage of these beams? These beams are actually having non-separability between spatial and polarization modes. You cannot separate the polarization alone. You cannot separate the spatial modes separately. So if you want to separate them, the intensity will be broken into this. I'll show that. I'll come to next that one. So these are called actually spin orbit beams, which leads to the polarization singularities, vector fields. Because we are calling it as vector field, because all the way the polarization is linear polarization. That's why we are calling it as a vector field, and it is defined in the same manner of the optical vertices, where this gamma is actually the azimuth of each linear polarization. If you are going from here to here, the azimuth of the polarization state actually changes when you are integrating about a point. You will end up with a one particular number that divided by 2 pi will give you the index of the point case, index of the polarization singularity. So this index can be positive or either positive or negative depending upon that the way you are actually combining the beams. So here I don't know whether this can be seen. You can see these are positive vertex and negative vertex with the left and right circular polarization will end up with if you are adding, just simply adding, it will give a radial polarization. But if you are subtracting with a iota, then you will end up with a azimuthal polarization. So the same combination can be realized. The same combination can give another set of two beams, which is having the anti-vector modes of radial and azimuthal polarization. So here itself, see, the two combinations can give the degeneracy of 4. 4 beams can be realized with that two combinations. So another set is this is the same. This is the Mach-Zehnder setup. In only one of the beam is taking the exponential of Im pi, this vortex phase. Another one is taking is a Gaussian beam. And if you are taking these, combining these two, you will end up with a polarization structure across the beam like lemon. And the another, if you are taking another set, then it will be a star pattern. So these are called elliptical singularities or C-point singularities. Why we are calling C-point singularity? At the end, at the center, the polarization is circularly polarized light. So around that, the ellipses are taking the azimuthally oriented. So like these structures. So the definition is again it is same, but with the index of IC. We are just naming it as the index of IC. Apart from that vector singularities, it is these singularities having hand in S plus or minus H plus or H minus can be either positive or negative for these beams. So how? So the properties of these beams. See, vector beams. If you are taking, this is the linear basis. If you are combining these two beams with a certain iota times or like that, you will end up with this is a linear combination of this one. Or if you are taking the in the circular basis, these vertex beams, two vertex beams, then you can end up with a you will be in the circular basis. But whether you are in the linear basis or whether you are in the circular basis, you will end up with the polarization of the structures only. It is just for representation, linear and circular basis, and to realization also. But the end product will be one of these states. So this is all the beams are having same intensity. If you are placing a detector on the beam path, so detector is not sensitive to the polarization and the phase, so it will only see the intensity. So these all the 4 beams cannot be ascertained. That the index value cannot be ascertained if you look at the intensity pattern only. So we are going for diffraction experiment. We have taken a triangular aperture on which these beams are incidented. So why triangular aperture? I'll show something here. So this is the positive vertex and negative vertex. Both look same intensity pattern to the detector. But when you are taking the triangular aperture diffraction, the orientation of these lobes will be varying like this. One is in this way, another will be rotated into 180 degrees. So like that, m is equals to 2 and m equals to minus 2. Both will having a 180 degree rotation. Likewise, m equals to 3. So if you count the number of lobes in one particular line, that tells what is the charge of your incident vertex. Like that, you can actually get the information of incident beam. But if you are coming to these polarization singularities, because these polarization singularities are the combination of plus vertex and minus vertices, and polarization doesn't affect the aperture does not affect the polarization, you will end up with a degenerate pattern. All the 4 beams will give this kind of, for m is equals to 1. So this kind of beam, for m is equals to 2, this kind of intensity pattern, m equals to 3, this kind of intensity pattern. So the equilateral triangular aperture is not giving any it is giving the degenerate states. We went for equilateral right triangular aperture, but here also all the 4 beams give same intensity pattern for different charges. But one thing we studied is the polarization pattern at the diffraction plane, which tells that a V point disintegrates into a C point singularity. As I told earlier, V point is vector beams and C points are the ellipse singularities. So a V point is disintegrated into 2 such number of C points that can be visualized here, which is the Stokes pattern and That polarization pattern is just difficult to understand, but the point here noting is this one, disintegrated into 3 points. So the degeneracy cannot be ascertained, and the intensity, the index values cannot be ascertained with the diffraction pattern alone. So what we thought, okay, so we want to search where we actually lost. So we lost here because the degeneracy existed in the creating itself, the degeneracy existed. So we want to remove the degeneracy by diffraction and polarization transformation. So what we did, this is the linear projection here. We take a linear polarization here that takes the linear projection. And here we take a quarter wavelet and a polarization combination, which is the irreversible possible of this one. So that will take actually a circular, left circularly polarized projection, and this beam takes the right circular polarization projection. So how we can detect the orthogonality in the linear projection like this? Azimuthal polarization will give an intensity lobe like this, and if it is a radial polarization, that will give a intensity lobes like this. So the index value, whether it is the positive index or negative index, can be ascertained in the circular basis, circular projection. So like that we did the experiment. This first column shows the orthogonality uh, indistinguishable distinguishable patterns of because of the orthogonality, and the lobes between these two actually tells about whether it is a positive index or a negative index. So this paper is published in optics letters long back. So what we have taken is this degeneracy is anyway existed, and the spatial and polarization modes, these two are actually non-separable states. So we want to use that in the image processing system. So how we can use that? So this is a spatially variable half-wave plate, which is having a that polarization axis of the plate will be rotated in such a way that it takes 0 to pi values. And we are actually using a simple 4F setup only. We are using a polarization input mode. And usually what happens for the detecting, for edge detection in one direction or other direction, you usually change this spatial filter here. But what we are doing, we are using the polarization as one of the parameter of the light. Without touching the system, the rest of the system, we can actually get the different orientation, different edge orientations. So that how we can do. This is what actually I told the spatially variable half wave plate. If you are incidenting the X polarization, you will with a radial polarization. If it is a Y polarization, you will end up with a azimuthal polarization. But at the end, that lobes actually, this lobes actually takes a rotation in the, from 0 to 360-degree rotation it will take. Like this. So this can be responsible for edge detection in that particular direction. Otherwise, this is the isotropic edge detection with these beams. So that like this. So we did that some simulation experiment in that. So we took a Ashoka Chakra as the image, and we can retrieve the edges along the X direction and 45 degrees and 90 degrees like that. And this is the isotropic edge enhancement using the circularly polarized light at the input. And this is the experimental results for the USF chart, and this is for red blood cells. You can see this is the PSF, and you can see this edges along that particular direction are enhanced. So that can be used as the Poincare beams or the vector vortex beams can be used in this edge detection methods. So conclusions, the diffraction of pole and polarization transformations are very important to study the spin orbital beams, and the spatial content and polarization content is are non-separable. So the interrelation between the phase and polarization that can be used in different ways, but one of the method we used, we come across with the edge detection of any particular sample. Thank you.
Thank you, sir. Any questions from the audience?
Thanks very much. That spiral faceplate that you showed early on in your talk, the experimental spiral faceplate, it has discrete thickness, discrete steps, or is it continuous variation? Because I was just wondering how you got the phase map to be continuous when you had discrete steps.
For the optical vortex, it is continuous from 0 to 2 pi. But if it is the HG mode, Hermite-Gaussian modes, it is only discrete. Either it is a 0 level, other side it will be a pi level. So the beam actually travels like this. So whether, I mean, if you are doing the undulation like this, it will go around like this, 0 pi Hg modes. But in the case of optical vortices, the beam actually, the phase takes the helical path and moves like this, because it's a continuous phase. There is no discrete between the two lambdas. I mean, the wavelength, whatever you are using, it is actually it sees as a continuous wave from the starting point to the tail end. So that actually creates a null intensity because of the interference from either side. If you are taking the helical wavefront from this point and this point, will destructively interfere at the center. This point and this point will be destructively interfere at the center, because these two are at 0 to pi variation. This is 0, this is pi. 0 pi. I mean, that phase difference is pi. That's why you are taking, you are at the center, the destructive interference happens. You will end up with a donut kind shape.
Uh, thank you for the talk, sir. But my question is, uh, you use that single single wave fronts, like plane wave fronts, and use the quarter wave plate to convert them to singular, right circular, left circular.
Yes.
Is there any property, like if we use like circular waves,
So
we can directly use like quarter wave plates to convert them to, if there is circular waves and we use quarter wave plate, then it again comes to right or left?
Yes, it will come, but the properties of the beams here, the spatial modes, the phase part of the beam and the polarization part of the beam are entangled. Okay, the moment you are putting a polarizer, it acts on the polarization. It not only acts on the polarization, because it is entangled with the phase. The phase is also affected. So you will end up with a lobes. In case of plane wavefronts, it is true, but in case of this thing, it cannot be done. But the way you are approaching to create the beams can be reversed and taken apart from that. That is what we approached here. If you see that. This, see, we are actually, what we are taking, this is a circular polarization state is coming. Another one is a left circular polarization is coming. We are combining with a quarter wave plate, right? Yes. Now these two, the polarization and phase, are entangled here. What we are doing here, we are reversing this process. A quarter wave plate and a polarizer we are taking, so that we can be decoupled. But we are using a diffraction to see the lobes. What are the number of lobes? That's it.
Thank you, sir.
Well, I was curious that are you really detecting a Stokes vector here?
I'm not getting.
You know, is the whole thing mirror matrix formalism? You know, when you're trying to model your system.
Yes.
Yes, and because you mentioned Bongara sphere, and it looks like there's a 4-channel here, or is that 4-channel detection?
I can't say it is like that, but as I told, the way we are combining them, we just reverse the process and use that beam, because this diffraction actually tells about what is the phase content in the beam. It's a simple diffraction with a triangular aperture. Mm-hmm. Okay, but we are taking the diffraction pattern to follow up the polarization. So you just, the diffracted beam is following the polarization, as the polarization says, okay, I have to take my left circular component to this way, and I have to take the right circular component to this way. That is what we are making with this combination. That's it.
Yeah, maybe I'll ask you more later.
Okay.
Because it's quite a complicated setup.
Any further questions? Thank you, sir.
Thank you.
The next oral presenter for the day is Dr. Geetanjal Deka, Assistant Professor, Department of Physics from the Assam Royal Global University. He'll be giving a presentation on resolution enhancement for deep tissue imaging with plasmonic saturated excitation microscopy. I welcome you on stage, sir.
Thank you. Very good morning to everyone. And I would like to thank Manipal University for arranging this IONS conference. And I would like to thank Nirmal Majumdar for inviting me and giving me opportunity to meet some old friends, my professors, and it's really great to be here. So today I am going to talk about resolution enhancement for tissue imaging, what happens when we try to image deeper in the tissue. So let's begin. So we know microscopy, right? Most of the students here are from life science department. So you must be familiar with microscopy. So what is the main, or what are the main factor or parameters that a microscopist are looking for? So if you think really, there are three main points. One is the contrast and the penetration depth, how deep you want to see, and another one is the resolution. Yeah. So I hope everyone is familiar with the term contrast. Contrast means I have this mic, it's black in color, so I put it in my black tie. It's very difficult to see, right? So if I put in a backside, so you can see it, right? So as if I put here, what you will feel is that the object is not there, right? So that is what contrast is. So in case of life science also, you need to have good contrast. So what do we do for contrast? Usually what we do, we use fluorescent markers or any marker so that we can differentiate the object of interest from the rest of the part of the material, right? And then another one is, the main thing is the penetration depth, right? So we have developed many other techniques by which we can go deeper, like you improve, you increase the wavelength, which can go deeper because of less scattering, right? And resolution, there are many different kind of techniques that has come up to solve the problems of resolution. And what is resolution is, if there is two objects together, if you cannot see them separate, then it's the problem. Resolution is not the problem of where the object is, it's the problem of the detector. So if you cannot see them, it means your eye cannot resolve them, right? So you need some other technique so that you can resolve. So if the images are separated enough so that you can see two different ones, then we can tell them they are resolved, right? So to have a good contrast, we need fluorophores or markers which are very strong and robust, which do not destroy over time, right? And give very strong signal. And for tissue penetration depth, what is our standard is, we want to see deeper than 100 micrometer or above. So above 100 meter, it is easier to see with other techniques. But above 100 micrometer is very difficult due to high scattering of the tissue samples. Okay? So resolution, what is the standard resolution? So what we say is lambda by 2 is the resolution limit. It means the wavelength you use, and if you half it, so this is your limitation of your resolution. So how to improve it? There are many techniques, right? So there are, what we will say is a better result. Why nanoparticles till now is very difficult to see with optical microscopy? It's because of resolution. That's why we use electron microscopy so that we can see the nanoparticles, right? But in case of bio, electron microscopy is not very good because you have to kill the sample. You cannot see a live cell with electron microscopy because it will die, right? So how we can see a live cell or live tissue by using nanoparticle as a probe or marker, right? So there are few super resolution techniques that can help resolve beyond the diffraction limitation, right? So one is structural illumination microscopy. Just before me, there is a talk about the beam manipulation. So structural illumination microscopy, they use beam manipulation to do different kind of imaging. And then there is one called localization microscopy. And there is one is a kind called on and off switching technique of fluorescent marker. And by using this technique, state microscopy, yesterday Professor Kao have talked about it, stimulated emission depletion microscopy. So it's a kind of stimulated emission technique. And yeah, that technique has already got Nobel Prize on 2014, right? So structural illumination microscopy is a wide field microscopy. Okay, so wide field microscopy has a problem that it cannot go beyond one layer. So you can only image a single layer. So if you want to go to other layer, it's it's impossible. Okay, and localization microscopy also a wide field imaging microscopy technique. So we cannot do optical sectioning. So optical sectioning means if you want to image 3D image, so you only can see one layer. You cannot see other layer. If you want to see other layer, you have to move it, right? So these two techniques cannot do it. So state microscopy actually can do it because it uses scanning techniques, but it has a problem that you need to manipulate the beam. So beam manipulated, just my previous talk, you have seen that you need a lot of modification in your setup to create a specific beam, like donut shape beam or different kind of how to say that wave fronts, right? So how simply you can get different kind of techniques. So in recent time, one work that on technique that's called saturation excitation microscopy. In short, is called SAX. Okay, so this technique has been developed by a Japanese group, and they have done it with a fluorescent bead. So they use fluorescent bead. They use this technique to do improve the resolution by using different harmonic signal. Okay? So I will talk about this technique detail later slide. So we borrow their idea of fluorescence, and what we did is, so we find out that when you use this technique for fluorescent beads, the problem is if you increase the application of your laser power, the beads can die out because fluorescence can be burned out. It's called photo bleaching, right? And that's why what our lab has proposed that we will use gold nanoparticles or silver nanoparticles, and they have plasmonic effect. Yeah. So yesterday we have learned about plasmonic little bit in a talk, that plasmonic is what is a electron cloud and surface electron cloud. They vibrate with your what wavelength you give, light wavelength you give. So depending on the nanoparticle size, so that frequency of, the wavelength of the light, if it matches, the vibration is more. So it's called resonance frequency. Okay, so if you put resonance frequency wavelength of light to the nanoparticle, the scattering is very, very strong. So it gives you very strong contrast. So you can do a very good imaging. Now we have high contrast. Now how to improve the resolution, right? So let's go how we can do it. So by this technique, actually, what we do, we use higher frequencies, right? So our goal is to improve the resolution, to improve the contrast, and to improve the deeper penetration, right? So this is a list where I saw that there are many techniques like SIM, so structural microscopy. So it can give you good resolution, but penetration depth is very bad. So one is STEP, which is the one of the best technique of higher resolution. It can give you very good resolution like 60 to 80 nanometer. It can go above 100 nanometer, but till now they have not achieved more than 120 micrometer. Even it has been achieved with adaptive optics only. Okay, so and Storm and Palm, they also are surface techniques, right? But plasmonic SAX, what I'm going to propose is that it can go beyond 200 micrometer, and if possible, if further work is done, it can be achieved below 100 nanometer. So yeah, it can be a best option for tissue high resolution imaging. So how SAX microscopy works? So for SAX microscopy, we need a temporally modulated light. So we use acousto-optic modulator, two acousto-optic modulator, and we produce a 10 kilohertz frequency of modulation in the light, right? And then we scan that beam above the leveling sample. It can be nanoparticle. So when you scan, actually you produce, when you scan, scan with a galvanometer or something, you produce a PSF. So this one is the PSF. So this one is PSF. It's called point spread function. It's actually the of your image of your nanoparticle, but is the its size and shape is mostly very much related to the your laser beam spot. So this one is can be obtained theoretically by using the delta function of your object and the Gaussian function of your laser beam. Okay, so this is your beam, and when you start on the modulation and scanning, so you have you seen that when you are at the when your beam center is not just above the particle, just above the particle, you get this outer rim, and when your beam is just above the particle, you get the center part, right? So center part scattering is very, very high. So you get saturation there. And from the outer rim, you get unsaturated scattering. So now what is saturated scattering and unsaturated scattering? So if you see, if you detect the scattered signal from the outer rim of the point spread function, your frequency, I mean the modulated frequency remains the same. So if your frequency is FM, this modulation frequency, so you get the same frequency, right? So we do the Fourier transform here. This is frequency domain, then it's time domain, okay? And then in case of saturated area, what happens is that your scattering is saturated, so you can get harmonic of that modulated fundamental frequency. So you will have if your applied 10 kilohertz is FM, then you can get like 20 kilohertz frequency light. You can get like 3 times and 4 times, right? So you can get harmonic generation of your modulated signal due to the property of the high scattering property of the nanoparticle. So yeah, by using this, you can actually improve the resolution. So let me tell you a little bit more about what is scattering. So let's see this curve. So if in x-axis what we put is your applied intensity. So if you increase the intensity, what we basically idea is the scattering should increase, right? Like a mirror. If you give light to a mirror, if you put high voltage light, you will get a reflection of more high voltage light, right? So if you increase the intensity of applied, so your scattering will also should increase, right? But after a certain value, the scattering is start to decrease. That's the beauty of it, right? So it decreases, so we call it saturated scattering. But if you further increase it, it can actually increase very drastically. So this one is a non-linear scattering process, right? So theoretical work is still undergoing in our lab, okay? So this can be seen by images here, right? These are nanoparticles. So these are images of the nanoparticle, right? Scattered image of nanoparticle. So when you are in a low applied intensity part, your images are very nice. There is no problem. There is very spherical. So if you plot this intensity curve, you have a very good Gaussian curve. But as you increase it, so this one is saturated, just saturated, right? And this, you see, little bit like a donut. It means the central part of the PSF, the saturation is, because of the saturation, the scattering goes down, but the other part is improved. And actually, if you increase further, what you will see is a concentric rings. Okay, rings of concentric, a lot of concentric rings. So you will have multiple scattering, multiple saturation, and saturation and resaturation. Okay. So how far you can go? So we have tested that you can actually get until 10 how to say, 10F frequency, and you can decrease the size of the PSF to 14 nanometer. So it is even smaller than the particle itself. So the image actually is not the particle, the image of the particle can be decreased to that one. Okay, it means only that part if you can select. How you can select? So you can use a technique called how to say that, lock-in amplifier. Okay, yesterday, if you are there, Professor Kao have talked about lock-in amplifier. I will talk a little bit about lock-in amplifier. So by using that lock-in amplifier, you can detect it. Okay. So yeah, this is our setup. So what it do is it uses a laser. So we split the beam into two, then we put two AOM, and we take the first diffraction. One is the +1 and -1. Then we combine them, and then we can generate a 10 kilohertz frequency modulated light. And then we use it by using a microscope, and put through the microscope we can scan the system, and we can detect it through a confocal system, home built confocal system, and we can form the images. And finally, this signal from here is go to lock-in amplifier. So what it do is you put a reference signal. You see that one of the part of the light, this is not going to the sample but go to the photo detector, which the light signal is converted to electrical signal, and this electrical signal goes to lock-in detection. So this lock-in detection, what it do, so it will read the reference signal, which is 10 kilohertz, then it can do all other frequencies. You can compare. So what is the frequency in comparison to your reference signal? And you can extract only that frequency, and you can form the image only with that frequency. Okay. So yeah. So what we do is, by using this technique, so we use tissue. Yeah. So we use secant breast tissue. We make thicknesses of different layers, like 50 micrometer, 100 micrometer, and 200 micrometer thickness of the tissue, and we put the nanoparticle above the tissue, and we wait for some time so that the nanoparticle can go through the tissue. So obviously it cannot go the whole layer of this tissue, but it's go a certain level, right? And usually what we do, we start to image from this bottom part to above part, how different layer can be imaged, right? And in one part, what we did, we put the nanoparticle in the glass slide, and we allow them to dry. We don't allow them to go through the tissue, so that we can maintain that thickness and the distance. And then we put the tissue then afterward, and we image through the tissue, and we see whether we can see that nanoparticles or not. So what we see is, when we put the tissue only and there is no nanoparticle, when there is only the fundamental frequency, you can see the scattered light from the tissue. Obviously, everything can scatter light, right? Only black hole cannot scatter light, okay, and black body cannot. So, but when we switch to 2F signal, we cannot see anything, because the tissue, I mean the breast tissue are not highly nonlinear. Okay? Some part of our body is nonlinear signal can give, but breast part of the chicken tissue, they don't have nonlinear signal. That's why we cannot see any light in 2F signal. But with nanoparticle, you see, if it is 1F signal, we can see both the particle and the tissue part. But when we switch to 2F, the tissue part do not give any light, so you can only see the particle. So by using this technique, the contrast can be very highly improved, and the background can be removed very easily, right? So this is from 50 micrometer thickness tissue. So we can see this is the scattered signal from the tissue part, and when we zoomed into part where there is nanoparticle, you can see there are a lot of nanoparticles, right? If you notice in this area, you see this part, you cannot know how many particles are there, right? It's because of the decrease of resolution through the tissue, because the tissue will scatter the light, right? But when you switch to 2F and 3F, you can easily see there are particle 1, 2, 3 particles are there, right? So by this way, you can improve the resolution, right? So what this curve shows is that how deep fluid half maxima of those per image of the point spread function is improving. So in 1F, the same particle have a very high, very large point spread function, and it decreases with the higher harmonic signal, right? And similarly for 100 micrometer tissue also, we have done that. And also 200 micrometer tissue also, we have done that. And we see that by using this technique, you can actually image much beyond 100 micrometer. So 200 micrometer is very easily achievable. And this is limit only due to because of our objective. So our objective's limit is 200 micrometer. We cannot go beyond that one. But if you can improve the NA of the longer focusing objective, then you can actually go beyond 200 micrometer. And if you use higher light, you can go even further. We use 632 nanometer. So if you can use 800 or something, you can go much beyond that. So this is a small result of, the incorporation of all those different thickness tissue. And you can see that the 1F signal with the thickness get enlarges very hugely with the increase in the depth. But by using 2F and 3F, the PSF can be brings down to very, very reasonable size, right? But if you can use like 8F, 10F, then you can improve a lot. But practically by using tissue, 10F is not easy to achieve. We are working on this part by using simulation. What size? Because the size effect of nanoparticle is very, very important for this one. So what size and what shape? We have tried gold nanostars, silver nanostars, and like spheres and cells, but nanostar have problem that it can get burned very easily. I mean, it do not burn, but the spikes can be destroyed with laser. So there are a few issues. So we are trying to do a simulation part, which nanoparticle will be good for imaging. And yeah, and this part is the ratio of the PSFs. And how is the improvement? So improvement actually is more very deep, more. Okay. So in conclusion, I would like to conclude that. So plasmonic sacks have a great opportunity to do resolution enhancement for deep tissue imaging. Yes, and it can give a very good background free imaging without any contrast issue, right? And we have seen that until 200 micrometer by using 2F and 3F scattering signal, we can get 2 to 3 fold resolution enhancement, and we have achieved more than 100 micrometer depth tissue till now, and we are still improving it. Yeah. And I would like to thank our lab members in National Taiwan University. This work is done in National Taiwan University Biomedical Optics Lab. And I have joined recently the Royal Global University in Guwahati, Assam. And you are all welcome to visit there. And we are starting to work in there also. So I have just joined in 6 months ago. Yeah. So thank you very much for your attention. If there is any question.
Thank you for a very interesting talk. So I'm trying to understand the physical basis of the technique. When you show that curve of scattering intensity versus whatever laser intensity or laser input laser, what's physically happening when the scattering intensity levels off or becomes more transparent, even though you increase the incident power? Is that been understood?
Thank you for this nice question, sir. Actually, our lab is working on it. There is a recent work they've done. They say that it's because of the temperature, the thermal issue. So increase of the temperature. So we are trying. I mean, our lab, one of our group of our lab, they are trying in 2 different ways. One is they are trying to do by this meteory. They are trying to solve the meteory, and one group is trying to solve the thermal issue. And while doing the thermal issue, they are also doing the absorption part. So I'm showing this scattered part, they're also doing the absorption part, because absorption part will give how much energy is absorbed. And if the absorption part also gets saturated due to thermal, then that will be that will explain this one, but it's still not solved. So they're
But
trying.
if that's the case, is there any danger for tissue imaging and that you destroy the tissue? And I wasn't sure what level intensities, powers you're talking about. Are these biologically safe, whether ex vivo or potentially in vivo, or do you know?
It's true, because it's a metal nanoparticle, it can heat up very easily by using laser. So for tissue, I think it will not be a problem if we, mostly this kind of technique is, actually I have a slide more, I did not show. It has been used in cancer treatment. So you use this kind of nanoparticle in cancer or tumor. So you use the laser, if it heat up, it's good. And you can see the area where the cancer is. And but for cell, I think this technique will not be very useful, because you have other techniques who can give you good resolution. Yes, so obviously more high power laser will be effective for that one. Thank you, sir.
Sorry, I think I missed a part. You said something about lock-in amplifier.
Yeah.
Yeah. What did you use it for? I think.
So
how did that help?
Yeah. So what we did is we divide our light into two. One light will go to the photo detector, so it will convert the optical signal into an electrical signal. So optical signal, we have 10 kilohertz frequency, so it will get a 10 kilohertz electrical signal. And one part of the light will go to the sample, so it will collect the scattered signal, and it will go again to the lock-in amplifier from a detector. So the scattered signal may have different frequency.
Okay, so
Yes.
just
So we separate out from this.
Okay, that's fine. So that's lock-in
Yeah.
detection itself. Okay.
You said about the chicken breast, so you simply reveal that it has got no non-linearity, and you have imaged through the fundamental frequency.
Okay.
Then when you go for the higher harmonics,
Yes.
so most of the part is blackened.
Yes.
Okay, and you do not image those nanoparticles, which you have said that they are all dried up.
Yes.
So why is that so?
Now, actually, when we go to higher harmonics, if there is no signal, it means there is no nonlinear material is present there. So if there is a signal, that means there is a nonlinear material. So if we suppose collagen is a material also found in body, it might have nonlinear property. So nonlinearity is actually not in the light. Nonlinearity is actually a property of the material. So if the material is a nonlinear, then it will give a nonlinear signal. So in my case, my nonlinear material is nanoparticle, and I put them in a nonlinear material. So when I use 1F, we can see signal from both the nanoparticles and the tissue. But when I switch to 2F, there is no signal from the tissue part, but only signal from the nanoparticle part, because it is highly nonlinear.
And even the FWHM, it is also shrinking.
Full width high maximum.
And
yes.
yeah, so in case of 3F, twice F,
Yes.
in F it is larger. Then as you shift towards the more harmonics, it is simply getting smaller and smaller.
Yeah, it's because what I do is that if I collect all the signal together, 1F, 2F, 3F, so you see the whole PSF. So what you can do, you can collect, because 1F can be get from all the part, but 2F can only go from the center part, not from the outer part. So when you take only the 2F, the outer rim is gone. So you only seeing the 2F part. So if you see the 3F, so they are more, you have to go more inside the PSF. So now you can see only the center part of the PSF. The other two, the 1F and 2F layer are gone. But in the 3F, you may have 4F and 5 and 6F.
Yeah. And the last one, and yes, what is the optimum size of the nanoparticles that you have dried up?
So our size is 80 nanometer.
80
nanometer, yes.
Okay.
We can use also like 60, we have tried, but 40, that don't give very good result.
Thank you.
Yes.
Yes, because the PSF is composed of different frequencies,
Yeah.
and a grating element actually separates the frequencies.
Or
PSF is composed of different frequencies, 1F,
yes.
2F, like so, right? The harmonics. And a grating element usually separates the frequencies spatially. So if you have a polychromatic line is falling on that, it will separate the lines that lambda 1 will falling at one particular position, lambda 2 will be falling on another particular position. So if you somehow can use this PSF falling on the grating, can you exactly relocate that central frequencies at one location and the outer frequencies at another location, so that your detection can be
More easy.
more easily and
Yeah, I mean, I have not thought that, but I think it's a good idea. If we use a grating, it's a different location, or we can use different
Yes.
reflector to reflect in different,
yeah,
right?
different detectors or
Yes.
the same detector with the different spatial locations you can actually
I think we
detect.
can do that too. But
that-
yeah, lock-in amplifier is, I think, more easy for us. We just put it and signal,
Okay.
just switch on 1F, 2F,
but
3F.
but that is after converting to the electrical you are using.
Yeah, we
But-
use PD, yeah, photo detector.
Yes, but the grating acts on the optical itself.
Yes, optical sense. Yeah, I mean, the electrical noise can be reduced, I guess. Thank you for this suggestion.
Thank you, sir. Thank you for your presentation. We now have a short break. You may proceed at the backside of the building for tea and coffee. All the delegates are requested to collect their coupons for the gala dinner from the registration room, and interested delegates for the social day tomorrow may register for the same. Thank you. The next session will begin at sharp 11:15.